So this morning, you got a little introduction to the fundamentals of meteorology oceanography and the relationship between the two. Now, I ask you, if you were sitting there, let's try to forecast what's going to happen. Sounds like a simple enough request, but just from the little bit you've seen, I hope you have a sense of the complexity of the system that we're dealing with. We're going to move right now to forecasting. And when I initially thought of this and talked it around, we were thinking about some of the differences between the federal forecast system and regime, not looking for anybody to give any proprietary information away, and the private. So we're really very fortunate this afternoon to have Ken Campbell from Commander's Weather, well known to many of you, and Joe Sienkiewicz from the Ocean Prediction Center. I've known Joe for a bunch of years. He's a fellow sailor, besides being a Fed. He's known on the bay. He was a merchant mariner in tugs, graduate of Fort Schuyler. So he's seen a little bit of all sides of it. And we are really very privileged this afternoon to have him here with us. Joe?
Thanks, Frank. Were you clapping because I'm a Fed, or were you clapping because I'm a sailor? Sailor, I kind of thought that. So what I want to do is give you a bit of a perspective. There's a couple things I want you to take away from this. Okay, one thing is the focus of a national resource, basically, of and I'll use the phrase contracting government, because that is the language that is in a certain document that's about 2 slides from here, or 3 slides from here. So I'm going to talk about that. I'm going to talk about the perspective of those of us that work providing information for the general use of people that happen to be out on the water. And the other thing, I want you to get a perspective of the complexity of the beast that we are trying to describe and warn you to stay away from. And I have a couple of slides like that. And the last thing, and it's probably about 5 more, but the last thing that I want you to start to understand some of the tools that we use, the perspective the forecaster has, and the importance of the tools that we have, the positives, and maybe even some of the, not negatives, but basically the restrictions, the limitations. I'm going to talk a bit about observations and the role of observations in the forecast process. I'm also going to describe, I'm going to spend a bit of time on one slide, and that slide basically describes the forecast process and how models are used, how they play into it, how observations play into that. So, in other words, strap in. Hopefully you'll get something from this, and I know I'm anxious to hear Ken talk also. We all went to dinner last night and had a blast. Guess what we talked about? Weather. Okay, so this is a view. This is a snapshot out of one of our workstations. Okay, this is how we look at wind over the ocean. This is from scatterometer data. I think it's from ASCATs, European scatterometers, radar, space-based. Measure the roughness of the ocean surface, and they infer the wind speed and the direction. Great instruments. There are 2. In September, there'll be a 3rd. And it'll go through its checkout phase, and sometime in the winter season. Next winter, we'll basically have 3 that are flying in a constellation. Ocean.weather.gov is our website. You should be used to it now if you've done any ocean racing or you're going to do any ocean racing. Ocean.weather.gov. Okay, so the world is divided up into areas of responsibility, and governments have basically taken on the responsibility to provide weather services over the oceans for various areas. The US has 2 areas. Met Area 4, the Western North Atlantic, from about the equator all the way up to 67 north, 35 west is the boundary, all the way out with Med Area 12, Bering Strait, down to the equator and out to the date line. And I'll show another slide right after this. And this is married up with a marine traffic display of the density of ships during 2016. So you get an idea where the ships are. And in the Pacific, guess where the storm track is? So they're impacted by weather all the time. In the North Atlantic, we see examples of explosive deepening lows and tropical cyclones. That's all in this area, in here, all the way out and all the way over to the UK. Again, ships are having to deal with weather all the time when they're underway. And this shows that. The US, what we've done is we've divided the responsibility down into several different offices. So my own office, the Ocean Prediction Center, has down to 31 north and down to 30 north in the Pacific. And because of history, tradition, and the character of the weather in the Pacific, we go all the way out to 160 east. Our sister offices are the Honolulu Forecast Office and the Tropical Analysis and Forecast Branch of the National Hurricane Center. And this little area right here is actually, the US was doing on behalf of the Peruvians, but the Peruvian Navy now has taken that on. So this is back, this box right in here off the Peru coast is Peruvian. But it gives you an idea as to, the world got together, basically through the World Meteorological Organization, and this is to ensure that people remain safe at sea and have the information that they need to make decisions. Okay, so, and I gotta read this from here. I can't read it, I can't see very well over there. Our governing document is the Safety of Life at Sea Convention. You know, you see the sticker on flares, you see the label on a life jacket, you see it on a life raft. Okay? It also basically is the governing document for providing a variety of different navigation services, ice services, a whole variety of different things. Chapter 5, US is a contracting government, and we're encouraged. One is to encourage basic collection of weather information at sea by ships. Okay? Another thing is to warn ships of gales, storms, and tropical cyclones. All those bulletins and everything that we produce, whether it's a tropical cyclone message, the forecast, high seas forecast offshore, is all under that right there. Okay. And then also to issue, at least twice daily, as appropriate, weather information suitable for shipping containing data, analyses, warnings, and forecasts of weather waves and ice, and shall be transmitted in text. There are describers, and I'll go to the next slide, as to why that and how that is done. And then also, as far as practicable, graphic and or in digital form. So they're both encouraged. Graphics enhancing basically the text, digital, grids, you call them gribs. That's just a file format. And now that would be like saying, with their .txt files, same thing as what a grib is. It's just a gridded binary file format, standardized across the globe. So graphics, you've seen a ton of the graphics that our office produces today, and then also in digital form, and I'll talk a little bit about that. Okay, how does that get basically, how does the services basically is described? So there's, based on that overarching in SOLAS, the World Meteorological Organization, basically the weather arm of and climate arm of the UN, basically through publication 558, everything that we do is described in here. So that's basically the governing document next to basically the overarching of SOLAS. Okay? SOLAS is pretty, you want to sit down and read something? It's pretty cool to read what our predecessors went through in trying to say how we keep you safe. Not we, how we keep ourselves safe over the ocean and the things we have to have and the regulations and all. Okay. This is the slide we're going to spend some time on. So, let me start here. This is Brad Reinert. Brad is sitting at our Atlantic High Seas desk. There is somebody there at a minimum of 20 hours a day, 2 10-hour shifts. We have 9 forecast shifts a day, 5 during the daytime and 4 at night. They're all 10-hour shifts. Right now, we have 18 forecasters, so they're rotating all the time.
I'm a branch chief, and actually my co-branch chief, Darren Figursky, is right up on the upper level up there. We went through a time period this fall where we were down numbers in forecasters, and our names were on a ton of the graphics that are produced by our office. I'm qualified to work this desk. I used to be on all, but not. And I want you to get a couple things to appreciate. One is the number of screens that surround him. There's 3 different computer systems here. This is one. This is sort of the one we use the most, called NAWIPS. This is AWIPS. All-weather, whatever. I never get the acronym right because it really doesn't really matter. Weather Integrated Processing System. And then this is just a PC over here. When we're busy flipping through, going up and down the layers that Lee showed you, or looking at different variables on the surface, we don't just look at sea level pressure and winds. We look at a whole ton of things to try and decide where a front's going to go, where a feature's going to be, where the lows are, and we look at multiple models, sometimes at the same time, sometimes on multiple different screens. Everybody sort of customizes it themselves, but the end product ends up being similar, so that you really shouldn't be able to tell what the difference is between the forecasters to a degree. Okay, so input, output. Okay, so the forecaster sits in the middle. There's a whole variety of different things I'll go through in a second that basically is the input into the decision process. But the forecaster is the focal point of the decisions. Okay, the numerical models don't make the decisions. The forecasters do. Okay, they add value. They have their own, they have experience, familiarity. We try to give the forecasters, part of my job, the information so that they can make intelligent decisions using the numerical guidance. Numerical guidance means models. Okay, simulations in the future, out into the future of what the atmosphere is going to do. Okay, they have familiarity, and they also, one of their roles is to interpret. Okay, you may have differences between numerical models. Do you split it? Do you go with one? Do you go with another? Is there a third? We have, I don't know, we have about 7 global models that we can look at, and then we have ensembles of models which are derivatives of those models in order we can look at probabilities, and you'll see that stuff in a little bit. Okay, so one key piece of the input is observations. Observations play a role to the forecaster. What's going on now? Critical, as we heard, out to a few decimal places, more than a few. They're also critical as input into the numerical models. We have to define the initial state of the atmosphere time and time and time again. In my office, we do, it depends on which computer system, but we do it at least 4 times a day. If not, we do it every hour, like over the United States. We're redefining 0 and using different data sets for that. In order, you have to know 0 in order to go out to hour 24, 48, 96, 386, okay? Different types of model. We already heard this morning. Deterministic. One model, one answer. The atmosphere isn't really deterministic because you go back to 0, we don't really know 0. We sort of codify it, but there are little error bars around every little piece of every temperature, whether it's instrument error or we don't quite have the height of it right, that kind of thing. Okay, it's not like it's just part of the nature of the business that every measurement has some sort of little bar around it. Okay, probabilistic means that we're using tools, typically running many numerical models in real time, with little tweaks to the errors that we know about the observations, or the errors, areas that we know that there's uncertainty. That, okay, we really don't have the number of observations in that area. Well, then that means, so what's our ground truth? We don't really have one. We have a previous forecast. So we basically use a previous forecast to help sort of tweak, we tweak the previous forecast with the observations, and then that defines the starting point, and then off we go. At the organization I work in with the Weather Service, that's 4 times a day we're running our global models. And there's a whole suite of models that we run at different times. Okay. We also use observations, we use in the numerical models combined to develop products that basically take the model output and then adjust to known biases. And those biases are determined from the observations. So actually, there's another step after the numerical models, and that is also fed in to the forecasters. So they have a variety of different tools that they're using. On the output side, obviously, warnings and forecasts, whether it's graphical, text, as we saw in SOLAS, or gridded. And our forecast range right now is about 1 to 5 days. Actually, it's 5 days, and we're hoping that's kind of a restriction that we really do need to go out farther in time. There's a connection back to the products, basically, observations. Basically, we use observations then to verify not only the numerical models, but also the products that we do. That way we learn, and we improve, and we get better, and we learn where there are gaps. Okay? So that's the forecast process. Brad did this twice in one day. He received 2 sets of numerical models, did 2 sets of analyses. His workflow basically is quite similar to this, observations to models. He starts with an initial state, an analysis done every 6 hours, and then does a suite of products based on that and the most recent numerical model. It's the rhythm, 24/7, 365. Okay. All right, and there's a variety of different products. This is actually, I figured I'd throw you a loop. This is the Pacific page off of our website. And analysis, forecasts, 24, 48, 96. There will be a 72 in here starting in March, once a day. And upper level, 500 millibar, surface, winds and waves, and this is wave period. So the T that Frank was just showing you previously. And this is a high seas forecast warning bulletin back to SOLAS. Warnings, storm warning, and then there's a description, 12, 24, and 48. That's because it hadn't developed yet at 0 hours, but it's expected to develop. We're always in the future. So, and that's basically the rhythm that we do. This is a very busy ocean. You'll see that later. And at times, we have up to 13, 14 warnings when it's busiest. And we manually do this still. It's not as automated as one would like. So it's a bit time-consuming. And we work in an operational environment. Everything is by time, deadlines, broadcasts. Doesn't make the broadcast, you just wasted your time because nobody who needs it is getting it. So we're driven that way. Okay, gridded information. So we're still in an evolution to producing information in grids, to having the forecasters interacting with grids. In the OPC, we're doing the West Atlantic, so there's a piece right here to a national grid. This is called the National Digital Forecast Database. This is wind speed, and this is the oceanic grids. And so we're contributing that portion, and then off the West Coast. There's between Alaska, Honolulu, and Guam, and American Samoa, there's 122 forecast offices that are contributing to these areas, to this patch quilt, basically, of gridded information. We do graphics that cover all the way out to here. We're in the process of gearing up to transition our production from graphics to grids to produce graphics and other things. So these gaps in here and in here, we're hoping to fill over the next 2 years. And we'll still produce the graphical products, but they'll have the baseline underneath of having the grids that the forecasters have interacted with. Okay. So a little bit of look into what Brad or any one of our forecasters will be looking at. This is 0 Zulu time. Everything is in UTC in our office. This is from the 5th, last Sunday. I think it was Sunday or Monday, one of those days, Sunday. And this basically, it's the GOES 16 imagery, infrared imagery. Actually, it's the geocolor. It's enhanced with the land underneath. And you can see, character of clouds here. This is Greenland. This is Labrador. Remember, we go all the way up to here somewhere. That's ice. And these are observations. They're a combination of ships. Predominantly, they're buoys, drifting buoys. That's what all these little symbols are drifting buoys that produce, like, for instance, right there, 1,029.8 millibars. And wind speed and direction, 35 knots out of the southeast. This is when we had a system coming offshore. And this is typically the tablet that our forecaster on the Atlantic high seas will be looking at, or it zooms of that. And so this is the analysis that Marshall Huffman, our forecaster, did using that type of information as input. So isobars fronts, the tracks for lows as to where they're going, and you get an idea, a little bit of the complexity. 3 different lows here, 1 here, 1,005 millibars, moving off to the northeast. Area of heavy freezing spray. You've learned about isobars. The wind up here is out of the west, up to storm force, and there's a little bit of a low right there. And you get an idea of, it's been frozen in time, of the fluidity of the atmosphere, and maybe a little bit into the turbulence, turbulent flow. And this is a frontal boundary down here that drapes all the way across. And there's a little low. We call this an inversion in the isobars. That's a trough right in there. And there's a stationary front, a weakening stationary front extending back to the west. A lot of information coalesced basically in this, in many, many different fields in order to put this information together. This is the wind field out of our GFS model, 0-hour wind field looking at wind barbs, which you're used to looking at. And you get to see that Marshall is saying that there's a storm up in this area, and in essence, there's right in here, there's about 45 knots via the model. So already he has evidence that there's wind higher than what the numerical model is saying. Southerly flow here, 35 knots. We already saw a ship observation of 35 knots in that area. And here's a nice big high, 1048, another one over, right smack on the Azores. And some up to 30 knots in the numerical model here off of the Iberian Peninsula in the northerly to northeasterly flow. We use this information a lot. I already had it in the first slide. This is scatterometer winds. It's a space-based radar on 2 different satellites. I already mentioned METOP A and METOP B. Twice a day, we get views like this over the Atlantic and the Pacific. They're polar orbiting satellites. So these satellites are flying, in this case, they flew up like that. And the instrument is on booms on either side of the satellite. It's a fixed antenna radar. It senses the ocean roughness. From the ocean roughness, and that's the small-scale roughness, you can infer the wind speed and the wind direction. So this is all color-coded. Anything yellow or higher, yellow, the amber, the brown, and then the reds, red being, the real red is actually hurricane force winds. Violent storm, basically 56 to 63 is in there. So in here, there's some amber, and then there's all some orange, basically, and some brown. There's storm force winds right there to the south of that little low that I was showing you. And a pretty good plume of gale force to strong gale force winds in the westerly flow coming off of Labrador eastward with that. Southerly flow in the Gulf of St. Lawrence, there's even some 45s in there, and some gale force farther south. You see sort of structures like this in the wind field often, because this is where the eddies are shed from the Gulf Stream, where there's warmer water, and also where the Gulf Stream itself is. And same thing here, southerly flow, and this is your Gulf Stream right here. We've got 35 knots of wind to almost 40 knots of wind over the Gulf Stream, 30 knots on either side, and then 25 to the south. This is our ground truth, because it's the most common data that we have. And that's what I want you to take away from that, is that we're sort of trained by the observations that we have. If the observations aren't very good, it's a real challenge trying to predict and actually validate what happened. It's just part of the process. We use ship observations as best as we can. They're not particularly frequent compared to something like this, where we get a data point at every 12.5 kilometer resolution. So we're kind of geared that way, is to use this data. And we've had experience using this data since the mid-90s, or data like this. Okay, and we know the limitations of it all. This is not our global forecast system, but this is the analysis, basically using observations for the same time. So this is basically the initial starting point for the next numerical model in 6 hours. We actually run this short scale model over the globe in a 6 hour, actually 9 hours. We run it out 9 hours, and we use the 6 hour forecast as the starting point for the next series of forecasts. Okay? And there's some similarities that you can see. You can see the strong winds up in here, You can see, well, maybe not so strong over the Gulf Stream comparatively. There is certainly gales up in the Gulf of St. Lawrence, and in the vicinity of the Gulf Stream, there's near gale, but not quite to gale. I'll go back and then come forward again, and you can see that there are some differences. There aren't gales, for instance, off the Iberian Peninsula, whereas the ASCATs did have a small area of gales and a really big area of 30 knots, or a little bit more than 30. Okay. All right, this is a little switch. We're out in the Pacific. This is yesterday, and we were commenting out on the floor about how noisy the Pacific is. So you're looking at many weather systems at many lows. Okay? There's a big low going up into the Bering over to Russia. There's another low on its heels. There's another low right there. Those are kind of the easy ones. There's a series of lows that are evolving right along this axis here. Watch. One there, one there. There might be one there, briefly.
What's the significance of the red?
Okay, so the coloration basically is, this is several different channels or sensing channels from the Himawari satellite. This is quite similar to our GOES-16 and soon-to-be launched GOES-17. The reddish and the brownish tends to be drier. The greens tend to be more moist. So this is kind of like combining infrared, visible, and water vapor. We found it to be really, really useful. And you get an idea of the low, like these are cumulus clouds in a low-level flow. They're ripping right along. Well, there's wind there. Okay, back in here, this is called a cold air development. It's back in the cold air. Spin, look at that develop right there. Okay, nice front forming, the complexity of the fluid. And right in here, we call this a bit of a baroclinic leaf, which means basically the potential for a storm development. I looked this morning, and the 6D analysis has this over in here, and that is anticipated to go hurricane force right up in this area today. And there are other spins. There's one there, and even you come up into the Sea of Okhotsk, and there's actually an area. Where is it in there? It's somewhere in there. Somewhere in here, there's a weak area of spin. The nature of what we're trying to describe. Okay? It's challenging. It's a little daunting every once in a while. The nature of it's changing because the tools that we have are getting better, higher resolution. We're seeing things that we never used to see before. Every once in a while, I hear a forecaster say, "What's that?" You know, and we go look at it and try our best guess as to what's going on. The nature of a fluid, a turbulent fluid. Okay. And for the same time, this is the scatterometer wind, so you get to see the various different features in the wind field. This is near storm force. There's that area of the westerly flow that I was showing you. There's that feature that with the nice little comma cloud with it, and you can see there's another low up in there. There's actually one right there, and you get an idea of everything is sort of going like this. And that's sort of the North Pacific. It's actually more kind of going like this, and then some of it is going up and over like that. And those are winds that are estimated to be at 10 meters above the surface. That's the standard that we forecast for. And this is the analysis that goes with it. So you get a flavor for all the different lows that are going on. I figured I'd give you a peek at the other ocean that we deal with. Okay. Probabilistic, well, before we get to probabilistic, I mentioned that the resolution of the information we're using is changing two different ways. The data is getting to be finer, meaning the distance between data points is getting smaller and smaller and smaller. So we're trying to simulate the atmosphere on the scale that the atmosphere really exists. Our global model right now is at 13-kilometer resolution. We output it at 25 because we can't really handle the volume of 13-kilometer resolution, and that's what this is. So this is the North Atlantic, and this is 12Z on the 4th. We're going to look at 120 hours of this in 1-hour time steps. So not only are we dealing with more frequent, higher resolution, we're also dealing with higher resolution temporally. So we're trying to see the atmosphere as a fluid. Okay, so same color scale. Yellow is gale. The amber is strong gale. Any browns are storm force. The scale is up here, and if you peak quick enough, this is going to loop. So peak quick enough, you're going to see some violent storm up in this area. 5 days, watch the weather systems. I'll let it loop a few times. Start again. Yeah. All right, I'm going to stop. So that's what we're trying to describe. That's what we're trying to predict. Is that what happened, is going to happen? Actually, that was a couple of days ago. It says what's going to happen. Pieces of that happened. Did it happen exactly correctly? No. Did it do a good job? A pretty good job. But there were errors all throughout that. And it may be that a storm system wasn't in the right place. We're kind of at the step now at 5 days. We know that where the storm systems are going to be. Pacific's a little bit more of a challenge. But the real challenge is the when and exactly where and the intensity. Okay, a couple more slides. Models are designed for different things. This model is called the High Resolution Rapid Refresh, or the HRR. It's run hourly. It's done for aviation because they're on that time step. One of the differences with this is it ingests radar data in order to basically capture precipitation. In other words, thunderstorms. It's built for convection, for thunderstorms. But in order to predict thunderstorms, you've got to predict everything else. So this is wind speed, just wind speed, 18 hours worth, and this is a front coming off the coast. This is the simulation, the prediction of the wind field. So there's a front that's going to come off right there. You see it in the last time step, off of New England. You don't see much of a signal when it's over land, but you see the winds intensify. These are gale force winds in southerly flow ahead of the cold front as it comes off. I put this in here for a couple of reasons. One, to show you the dynamic nature. The second is the Gulf Stream. That wind max down here, that blue that then goes to green and then has some yellow in it. Well, I guess it doesn't have yellow. It has to a darker green, okay? That's your Gulf Stream. So the Gulf Stream plays into the atmosphere. It kind of works the other way also. But higher winds along the Gulf Stream over warm water with this mixing. So the Gulf Stream has a significant role in the atmosphere, basically in weather prediction. Okay. Probabilistic information, these are probabilities of gale force winds. And I'm going to let this loop also. It's a different time than this. And this is on a link on our webpage. I think, Frank, you showed it earlier. Okay, so I'll let you see how this goes. So the reds are very high probabilities. The probabilities are over here. And this is through 240, this is through 10 days. It's a quick loop. But you can see that over time, the colors, you don't see red as dominant anymore. You start to see the color scale drops because the probability drops as you get farther out in time. The models that contribute to this 40 models, actually start to diverge. And they diverge in intensity. So you start to see that right about there, that you see, okay, there's little pulses of higher winds, but there's a relatively low probability of exactly what the wind speed is going to be, 34 knots or greater in that area. This is inherently what the atmosphere is in order to really predict, we really should be giving you, well, there's a 25% chance. And you really don't want to hear that, but that's the reality of the nature of the atmosphere, because we don't know exactly 0 hour. Okay. Couple more slides and then I'm done. This is GOES 16. This is our January 3rd and 4th storm. And I want you just to get an appreciation. This is imagery every 15 minutes. Yeah, did I do 15? I did 15. And you're going to see the development, explosive development of a cyclone. Snowstorm to you, ocean storm to us, of hurricane force strength. These little things here, the green colors and the reds, that's the density of lightning strikes. Okay? Nature doesn't fool around. Bomb, now you know why Fred Sanders and John Jackham called them a bomb. They're also called wave cyclones for a reason. See that roll up? That's a wave. Just another atmospheric wave in a different form. It's a thermal wave. Now let it go one more time. You can see in the cloud structure early on that where these low clouds are, it's basically where there's warmer water, where you have cold air over warm water. Stationary front draped in here. You can see the thunderstorms around that. And watch, this is all going to lift northward as the 500 millibar trough digs down. It's right back in here and starts to arch and come out. Convection in there, and then watch, right there. That's where it's all happening. And we know right in this area of that comma is where we typically see the extreme winds. So right in there. Okay, let me go to the next one. We're playing with things because of the information we have. One of the things that we're sort of playing with is trying to take those hourly time steps that I showed you and composite them. So this is basically the maximum wind over a 24-hour period for the storm that you just saw, ending at the last time period that you saw. So this is a little different time scale. So near gale is green, yellow is gale to strong. Strong gale is orange, like a brownish. Red is storm, and then purple is hurricane force. So this is just model output. This shows you the complexity of the wind field of the numerical model in a 24-hour period. This also shows you that we had better have had gale warnings for that area, storm, and that's the maximum wind out of the numerical model at 10 meters, 84 knots. I wrote a forecast of 65 to 85 knots for this storm. Unfortunately, we could see through marine traffic, there were ships in here.
Joe, is any version of that available to the public yet?
Not yet. We're still thinking about it. We're still sort of presenting it in this form, but that's a good question. We can do that, but it's direct model output. The reason why we use it is because it's hard for us to evaluate everything in the time that we have. So using composites like this, at least we can see that there are maxes of wind in certain areas. Okay, two more slides. So one way that we're going is that to try and interact better with mariners, safety, and this is from the IMO, International Maritime Organization, basically, is a mandate, is decision-making tools for hazards into the electronic display information systems. And we have basically an international working effort on an international team that we're hosting. And the idea is basically to deliver hazard information into the ECDIS in order for ship operators to make better decisions. It's still a few years away, but we're working through, it's really dog work, in order it's all the details, spreadsheets, all kinds of different things for every weather element so that it's integrated into their systems, sort of the same way that we do business in our own office. Again, it's encouraged by, actually, it's mandated by the, not exactly mandated, but it's really encouraged by the International Maritime community in order to bring things in. And we're trying to figure out, working with the teams, to how to do it. So, observations are absolutely critical, and they take on a whole variety of different character. They're satellite-based, they're conventional, meaning surface observations, ocean obs, both on the surface and into the ocean. Okay? They define the initial state, and they also are used to validate the forecast. For verification, they're the basis for improvements. Okay? Numerical models, atmospheric, ocean, waves, ice, etc. Okay? That we use all of them. And in the deterministic mode, high resolution, even on the global scale, on the regional scale. We even do storm scale for hurricanes. We run specific models for a hurricane. Okay? Probabilistic for confidence and also for likelihood. And we run what we call coupled, and we're just starting in this realm, where basically we're modeling the Earth system. We're not doing these pieces separately. They're actually basically all talking to each other and run coincidentally. Okay? And this is sort of the next big step forward, and it's ongoing, and probably the next 3 years, I think, is where we're at on the global scale that we'll be running fully coupled systems. Forecasters still have a critical role in the warning process, in the forecast decision process. And our role is changing a bit because that's really what we're here for, is to keep you safe. Gale, storm, hurricane force, tropical storm, hurricane, freezing spray are our warning categories. That's our mantra. That's what we're focused on, just to give you an idea. And there are challenges. Rapid intensification, both tropical and extratropical storms. Yeah, I just showed you, was that forecast perfect of what I just showed you in the imagery? Not quite, but it was pretty darn good. We knew that was going to happen. If you were one grid point here or one grid point there, okay, that detail may not quite be right. But we're getting the character of that certainly down at this point. We're still struggling with this layer of the atmosphere against the surface called the boundary layer. Okay? We're struggling in a sense because it's noisy, it's turbulent, and it's where all the interchanges occur. So there's a focus on that, both on the physics, the structure, and the interactions. And again, observations at representative scales are a challenge, both in the ocean and the atmosphere. We can't make something from nothing. It's not alchemy. We have one point, and all kinds of things are going outside of that point. It is a challenge for us to basically observe and also to predict. So let me finish there. Thank you.
Time for a question. Perfectly clear. That's perfect.
Joe, a question relative to your forecasting and what we hear about the European model, the accuracy and reliability difference between the two.
Well, every model, well, we use all of them, to be frank. So let me just start that way. So when we're doing forecasting, we're using basically everything we have available to us. European and the GFS, we've evolved differently. They have been very focused on a specific time range, what they call a medium range. They also have been very, very good at defining 0 hour. I think in the US, we have so many weather problems, and we basically are trying to model and predict for the weather problems, because the Weather Service is an end-to-end service. The European Center does modeling. So I think there are differences. I think there's pretty good evidence now that actually, especially this winter, that those differences are getting closer and closer together. But there have been inherent differences. It's not just the Europeans, the Canadians, UK Met Office, Japan actually has a very good global model. The good news is we share information.
after.
Okay, so we're not balancing one off or another. We're basically using the information to try and get the best information to you. I hope I kind of hand waved my way through that. But,
He's good.
yeah. Actually, you had a hand up next.
I guess on products like SailFlow, you can select different models and you see different things. Is that the best available source to see some of this direct data for a person who isn't in the Weather Service?
I'm trying to think how to answer that. Okay, so basically, he mentioned specifically about SailFlow, and basically you can select a variety of models from SailFlow. There are a variety of different viewers and that sort of thing. Make sure you know what you're looking at, like what numerical model it is, so you're not just, oh, that model, du jour of choice or whatever. I would look at multiple models. I also would balance on the display capability. I mean, you can have a great model, and if you can't interpret it, it's not going to help you at all. Make sure you're comfortable, like the color scales. Did you get what you want out of the display? I shop around too. I don't just look at our stuff, and I sail. And yeah, I would kind of factor that in, and then prove it out. Okay, there's a wind shift coming through at such a time. Did that happen? I mean, my experience, I like to use the HER when I can, when I'm sailing, and the character of the wind is pretty good. The timing of the shifts are pretty good, unless there's thunderstorms. The strength of the wind, especially if it's stronger wind, may be a little bit too weak. But I can time things. Okay, eventually we're going to have to do something, put a reef in or that kind of thing. Anticipation to be ahead of time. So I guess I want to answer it that way. How many more? Oh. Okay, so let's not short Ken his time.